The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you. In other words, I'm a geek. So, anyhow, I'm here to talk about reinforcement corrosion. There's no perfect solution. You know, one of the things I learned from Tony, one size doesn't fit all. You have to understand the situation, what's going to work best for you. I ran into Tony when he was with 546, and he convinced me to get involved in 563, and oh, what a lot of work that was. So he was good at conning you into doing things. Anyhow, concrete and reinforcement steel, there's a strong connection. It's a nice synergy. Steel strengthens concrete. Concrete's weak in tension, steel's strong in tension. And in turn, concrete protects the steel. The high pH of concrete creates a passivating layer around steel. Everybody's happy. Until bad things start to happen. Unfortunately, all steel reinforced concrete is at risk. Steel is just thermodynamically unstable. It is going to rust at some point. You can't change that. You can do a lot of things to prevent it, and the real trick to being successful is to keep it from rusting until you retire. Cost is about 1 to 5% of corrosion. That's all types of corrosion, is 1 to 5% of the gross national product of a country. A lot of money. Just of corrosion mitigation in steel, it's estimated to be $1.25 billion. As long as we reinforce concrete, it's going to rust. You're installing a time bomb. You may be able to do some things to keep it from happening, like impressed current cathodic protection, but eventually the power is going to go off. So natural laws, concrete cracks, steel corrodes. It's an electrochemical process. The passivation layer, due to the high pH, is actually a corrosion product of the steel. It forms very rapidly. It's just insoluble. And until halide ions, chlorides, bromides, iodides, reach a certain level, that says here 330 parts per million, it's a moving target. It depends on a lot of things. A pH value falls much below about 10, corrosion will start. And it also depends on the oxygen, the temperature, the resistivity of the concrete. What happens? Steel expands when it oxidizes about 4 to 6 times, more or less, the volume. It's in a low tensile strength medium of concrete. That expansion causes cracks. Once concrete cracks, all the properties get compromised in a hurry. Why does corrosion occur? Well, we start out with iron ore. We pump a whole bunch of energy into it in a refining process to turn it into steel. And then Mother Nature wants to turn it back into iron ore through deterioration. So what can we do about it? We can prevent it, change the nature of the steel, replace it with an alternative reinforcement. We can provide protection, creating a barrier between the hostile environment and the steel itself. Or we can try to mitigate corrosion. However, rust is going to happen, and the seasonal apocalypse is upon us. Spring, we have de-icing salts, we have warming temperatures, we have lots of water. Corrosion management combines 3 really neat things: the economy, the environment, and social responsibility. It is a key component of sustainability. For corrosion to occur, we need 4 components. We have to have an anode, a cathode, electrical path for the electrons to flow, and an ionic path for ions to move through the concrete. We can do different things at different points. For the anode, we can affect the concrete permeability, changing the water cementitious material ratio through pozzolans, chemical additions. We can change the corrosion threshold through inhibitors. We can reduce the reactive surface like with coatings. We can force the opposite reaction with cathodic protection. At the cathode, we don't really see a whole lot of things happen, but it's still an essential part of the corrosion cell. Again, we can reduce the active area of the corrosion surface. We can dry out the concrete. We can use inhibitors that are effective at the cathode. And again, cathodic protection. For electrical continuity, we have to disconnect the anode and the cathode. Best example of that is like a coating on the reinforcing steel. There's no place for the anode and cathode to form unless that coating gets damaged. The ionic path, we can change the resistivity of the concrete. This is ions moving through the concrete, supplemental cementitious materials, drying the concrete out. When you think about it, all the deterioration mechanisms in concrete, once I've got the concrete properly cured, if I can keep the water out of concrete, a lot of really good things happen. I don't have alkali aggregate reaction. I don't have sulfate attack. I don't have ingress of chlorides. I don't have corrosion. So we have to break the chain, either through mechanical or physical means, or through electrical means, or chemical means. In corrosion control technologies, prevention can be alternative reinforcement. I also consider corrosion inhibiting admixtures in concrete a form of prevention. You do it before the corrosion occurs. You're no longer fighting against Mother Nature as much. It's not an uphill battle. The longer you wait to try to control corrosion, the harder it gets. And unfortunately, concrete's such a great material, we usually let the patient be about ready to die before we do anything about it. Protection, membranes and coatings, penetrating sealers, rebar coatings, increased cover. And mitigation, surface applied corrosion inhibitors, galvanic anodes, electrochemical chloride extraction, electrochemical realkalization, and other electrochemical means, cathodic protection of impressed current or distributed galvanic anodes. None of these is perfect. That's why we have them all. I'll go through all of them. Non-corrosive reinforcement. It's really great. It's permanent. It eliminates corrosion. Unfortunately, it costs a lot. Design may be different. It may develop differently, may have different yield strengths. Is it compatible with conventional reinforcing? You get too noble, like try put carbon fiber in contact with steel, it's going to cause the steel to corrode. What about if I'm using epoxy-coated rebar and I've got pinholes or voids? What about the bond that forms on galvanized rebar? I've got a corrosion product that develops, and that's going to change the way it bonds to the steel. Here's one estimate of cost difference, upfront cost. Look at how much more stainless costs, 2.5 times more than black bars. But if you look at the time it takes to repair, stainless is over 100 years. Conventional reinforcing, 20 years. And everything in between. Or if you look at the life cycle costs, conventional steel has the highest life cycle cost. And stainless, one of the lowest. Epoxy-coated reinforcing in this study also worked very well. Admixtures. There's a lot of different kinds. I've been playing around with cement and concrete chemistry for most of my career. We can come up with a lot of theories about how and why things work, but they're theories. Anything you do to try to analyze what's going on in concrete changes what you're looking for. Admixtures are preventative, they have a usage history, and they are in intimate contact with the reinforcing steel. However, do they stay in the concrete where you want them? Do they leach out? How do I verify the dosage? Trust the ready mix supplier, I guess. What about dispersion verification? Did they all get mixed in the way they should? Many of them are concentration dependent. That is, do I have enough of the stuff in there to really do me any good? Do they get consumed during their inhibition operation, such as nitrites? And they're proprietary. Us material suppliers don't really tell you a whole lot of what they are sometimes. There's organic and there's inorganic inhibitors. Increase cover. Make the concrete thicker. It's renewable. I can always make it thicker if I can take the dead load. It's inexpensive, and it's possible to enhance the adherence, such as with a anti-carbonation coating, for example. I paint the wall. Downsides, they're consumable. It doesn't last forever, such as for coatings. I do increase section thickness, I can increase the load. The defects, if I have defects in my protective system, I can actually make the problem worse. And it's detail and inspection intensive. Examples of this: wall coating products, structural repair, surface repair. Membranes. I can improve the aesthetic appearance of a structure. They're relatively inexpensive compared to replacing the structure. They have a fairly long life. They can be recoatable and repairable. The downside: many of the membranes are reactive chemistries. They require a dry substrate. How dry is the concrete? They require surface preparation. That increases the cost. They are maintenance areas. I have to keep them intact. Abrasion, coefficient of thermal expansion differences may affect them, but snow plows are the biggest damager. Snow plow scrapes off the membrane, you now got holes, de-icing salts getting in. They may also trap moisture because they're impermeable. Fill the concrete up with water and let it freeze, bad things happen. I've got total saturation, my air void structure may wind up not being effective. Reinforcement coatings, they can be applied in the field. They're fairly low cost, pretty mature technology. Some claim to be bonding agents. My personal opinion, even though we sell them, hard to beat. Just a good scrub coat, have proper surface preparation, take your repair material, mix it to the consistency you'll use it, scrub it into the substrate, take the aggregate that doesn't fit in there, get rid of it, and now place your repair material before it dries out. The downside of reinforcement coatings: how do I get them underneath the steel? It's real hard to reach there. What about pinholes? What's their bond to concrete window? The longest I know of a bonding agent lasting is maybe 24 hours. The studies I've seen on our products and other people, you start out, it's pretty good. The longer you leave it open, the worse it gets, and after 24 hours, not so good. Continuity of the coating. And their rate of hardening depends on the environment. So their chemical reactions, hydration reactions for setting up, so in cold conditions, they don't work so well. Do they do anything about the incipient anode, the ring anode, the halo effect? That's where the concrete, the steel that was corroding, was the anode of the corrosion cell. And right outside where it was corroding is the cathode. But I don't see anything happening at the cathode. So I excavate out the hardened concrete, I fill a hole where the anode was, that makes that cathodic. And it moves the anode to right outside the repair. And by making it more cathodic, I may make it worse. Penetrating sealers. My opinion, silanes are one of the biggest bangs for the buck you can do for the good of concrete, because they dry it out. They're renewable, they're inexpensive, they don't change the appearance, and I can teach the dumbest guy on your crew how to apply these things in about 30 minutes. They're easy to apply, and it's hard to screw it up. Keep it off the vegetation, keep it off the windows of the cars. That's about all you got to do. And they do repel water. However, they're consumable. Nobody can really tell me why they go away. We just know that they do eventually. So that creates a maintenance situation. When do I reapply it? How do I monitor their effectiveness? They don't do well against high hydrostatic pressure. So I can overwhelm that hydrophobic effect, such as in immersion situations. How wide a crack will they bridge? Not very wide. And many of them are solvent-based. All of the silanes and siloxanes, as they react, generate VOCs, volatile organic components, most of which are alcohols. So it smells like vodka when you apply it. Just don't smoke when you do. And overspray, like I said, plants don't play nice with silanes. We also call them water repellents. Surface applied corrosion inhibitors, very controversial topic. They're renewable, they're fairly inexpensive. They don't really change the appearance, they're easy to apply. It works by magic. They're inhibiting. They're not solving the problem. They may slow it down, they may not. Your choice is, if I have a lot of corrosion going on and I use one of these, it's easier to apply than ripping out the concrete and doing more invasive procedures. It may help. It may not. How do I monitor their effectiveness? How deep do they penetrate, and at what rate do they penetrate? What about the residue left behind? Some of them do leave a residue and can inhibit bond. Some of them don't seem to harm bond. You have to test it and see. Their volatility. If I have a vapor phase corrosion inhibitor, it moves in a gaseous phase. Does it move into the concrete or move out of the concrete? Probably a little bit of both. Many different technologies, again, they're proprietary. We don't tell you what they are, just trust us, they work. And what's their life cycle? Galvanic anodes. Two real kinds. There's discrete and there's distributed. These work like galvanizing on steel. So the zinc corrodes preferentially, the zinc is the anode, and the steel becomes the cathode. They're really an electrochemical method. Their advantage, they're a point source, or the distributed ones can be general protection. They follow the corrosion activity, so it's like self-regulating. They don't require an external power supply. As the corrosion of the steel wants to increase, the corrosion rate of the galvanic anode increases to keep up with it, if it's properly designed. I can monitor their effectiveness, but I have to design it that way when I install them so I can monitor the corrosion current. So you have the anode, and you have a junction box, and a wire from the steel to the junction box, a wire from the anode to the junction box. You join them in the junction box. Now I can do some monitoring. Otherwise, I really can't. And the discrete anodes, the little hockey pucks or the small ones, do a good job from everything we've seen at inhibiting the ring anode, the incipient anode effect. And they're self-powered. They're consumable. I got something that's going to corrode away, and eventually it will wear out. Do they passivate? In that chemical environment, you have to put some stuff in there to keep them active, but often that stuff that you're putting in there may wind up leaving corrosive material behind when the zinc's gone. They attract chlorides as they corrode. And I have to excavate to install them. And oxidation buildup. However, with things like arc spray, flame deposited zinc on the surface, that's pretty cool technology. It changes the appearance. I have to have dry concrete, and it's some pretty specialized equipment, but it's been pretty effective. Impressed current cathodic protection, you take a course at NACE, they're all over this. They love impressed current cathodic protection. It works. It's got a long usage history. A lot of different systems, a lot of different designs. Downside, really expensive. It's got to be designed, installed, maintained, and monitored correctly. You don't do any of those 4 steps, you're screwed. Pardon my language. You have to have continuity of the reinforcement. So if I hook up one of these systems and I don't have all the steel connected, guess what? I just forced the steel that ain't connected to rust like crazy. You'll find out in a hurry. And if I crank it up too high, I generate acid at the anodes and I destroy the concrete. If I crank it up too high, I may also kick off alkali aggregate reaction. And if I turn it up too high, I may generate hydrogen. And if I've got post-tensioning or pre-stressing around, you don't want hydrogen. It makes it brittle. And you don't want brittle in that stuff. And it changes the appearance. So anyhow, the best thing I can tell you about corrosion, follow good trade practices, such as the Manual of Concrete Practice from ACI. I love this acronym DDAS. Don't do anything stupid. Use a relatively low water to cementitious material ratio. And I say cementitious material ratio, I like pozzolans. They do good things. Have satisfactory material quality, enough binder for strength, consistency for consolidation, enough cover, cure the concrete well. And after that, keep the water out. On the other hand, entropy. You're fighting against Mother Nature. The steel's going to want to rust. So it's not so much about letting it go as submitting to the inevitable. Concrete maintenance. We ignore concrete once it's cast, but it really should be maintained. You buy a car, it comes with a maintenance manual. One of the most controversial things in the 562 repair code is a requirement to have a maintenance program provided. You have to verify that the repairs that you have installed are working. You have to inspect that things were done correctly. As soon as you got a crack, fix the crack. The longer the crack's there, it ain't going to get better. Yeah, you heard about autogenous healing and fancy bacteria and fungus that'll deposit stuff. Ain't there yet. Ain't ready for prime time. You got a crack, fill it with something, keep the water out. And don't delay because the problems get worse. So that concludes my presentation. You see my hair getting gray and my baldness appearing. I'm now an old guy. And I didn't bring the Tony Murray tan turtleneck. But yes, I did. Thank you very much.